Thank you very much for the organizers actually for setting this up. I think it's a really nice workshop. Let me try to get rid of this video panel here. There you go. I think no, it's fine. It's just like I had this big zoom control in front of my screen. So yeah, thank you very much. And so I don't want to brag here about this, but actually this is what you're legally obliged to do, right? So the EU tells you have to put the logo. So like, I'm sorry, but of course I love the EU because they fund us, right? But I should thank a couple of people before starting. And so this is joint work with my former PhD student, Leonie Neuhäuser, one of the last projects that she did in her PhD, and with my PhD student, Michael Schulkemper, and with Francesco Tudisco, who is actually an Alan Turing fellow from Edinburgh now. All right, so let's start. So I don't want to talk about algebraic objects this time around. I thought I'll mix things up. So, but before getting there, so I want to talk about hypergraphs. But before getting there, I thought like, okay, let me try to reflect a little bit on the different types of modeling paradigms, let's say, that we've seen in the last couple of days. And so there's one paradigm I would say that's relatively common in network science for sure. Originally, they're basically when you think about networks as a model for relational data. And what I mean with this is that we measure edges, we measure connections, we measure relations between, let's say, people, right? And so the classical example is relations of people in social networks, and your task is maybe to find communities, right? Or here's another example where you have citation patterns between patents. So patents cite each other as well, and your task is to analyze the central ideas, so the central patents who came up with the most central things. And so there's a generic goal, and the generic goal underpinning this is basically that you want to analyze a model and understand connectivity patterns in these complex networks, right? And so the connectivity is the data. And I mean, why do this, right? Because of course the idea is that the functionality of these complex systems leaves some sort of footprint in the connectivity pattern, or the other way around, the connectivity pattern constrains what these complex systems can do. If you think about synchronization, for instance, that's clear. Like if you have some obstructions, some topological obstructions to synchronization, or to spread of information, right? You might have a bottleneck. And then there's this sort of second perspective, and of course I'm putting them as separate, but in reality they're not so much separate. Often they're sort of entangled, and that's where we don't think about the data as the relations, but the data is that thing that lives on top of the topological space. So Sergio, for instance, talked about topological signal processing, where the signals live on top of a topological space. And that space can be a graph, but it can be a higher order hypergraph, for instance, as well. So synchronization, looking at Christian, big here over there, right? So you have a data, you have a dynamics on top of a arbitrary but fixed network. And so maybe you have a model for opinion formation, and your task is to understand the long-term behavior in terms of, let's say, polarization, what have you, right? Or synchronization. Or you have a social network with node attributes, and this would be now the machine learning approach. It's not dynamical data, but it's maybe attribute data, right? And I want to predict Pietro's opinion on something. I know my opinion. I know Ginestro's opinion, maybe, and Jürgen's. And because we're talking to each other at this conference, we made bihomophily, so trying to predict what his opinion is, right? So, and here the generic goal is basically now to leverage the underlying structure to make predictions about the data that's supported on top of the structure. So we want to understand, again, the complex system, and now we have a different entry point, if you wish. We're not measuring on the scaffold, on the connection, so we measure something on top. And yeah, so this is, I would say, there's two kind of themes that I liked. Like I tend to think about these two things, but of course they are getting entangled, right? And well, if we are talking now about hypergraphs, we of course want to go beyond graphs, right? And so I like this picture here to think about. If you think about classical signal processing and machine learning, then the underlying domain was basically Euclidean, completely regular. It was, in some sense, boring. We never really thought about it, in fact, right? We took it for granted that it has this regular structure. And then with this sort of advent of network science, graph-based machine learning, and so on, we suddenly realized that, oh, the graph structure has a lot of interesting information. It's important to understand what's going on top of this. And of course, to understand signals, you know, there's a rich interplay between these two things, right? And now the next step, arguably, in this workshop and in many other instances is to go beyond, right? So to go to cell complexes, simplicial complexes, hypergraphs as the scaffold on which things happen, but then to have a richer type of data, right? So you have data that is not only associated, let's say, to points in space, if you wish, but also to line segments, to areas, and you can make this abstract if you want as well, to sets, right? Okay, so this is the picture basically that we have, and we're talking about going from here to here, right? But then the problem is, or let's say often, I'm kind of like when I present this and people say, so why do you need all of that? Can't you just always work with a graph, multipartite, bipartite, whatnot? And so I get a lot of different types of questions on this, but we'll start with a short prelude on some of this, let's say, things in defense of why we are doing this. But for this talk in particular, I will focus on hypergraphs now, not because they are better, but just because, in fact, I tend to work more on cellular and simplicial complexes, but hypergraphs turned out to be our tool of choice here. And so we're thinking about network dynamical systems and higher order dynamics. And so what we have is a state vector X. Then we have a nonlinear dynamical system F that is, you know, has a state vector, of course. So it's but it also, we allow for an input, let's say, in general, right? So now what I want to study here, rather than distributed signal processing or distributed machine learning, is distributed dynamics. So structured dynamical systems, right? So we have state variables of state vectors xk, and they are assumed to be localized. And when I say localized, I sort of put it in quotes, because I mean, they are attached to nodes. They could in principle be attached to edges and areas as well, but sort of the area is not the whole system. It's something that's sort of localized, right? So if you think about it in terms of physical space, this is something that you can measure at a particular small area. And these nodes or state variables, they interact with each other. And this is what this system describes. So in other words, we have to put much more structure in F, right? And so here is, let's say, a variation of such a, what I would call a network dynamical system here. So a state variable gets associated to every, so xk is the state vector of the kth node in here. It has some self-coupling. So this is the stuff that this node does on its own. And then we have here, now this is a linear expansion. So this AJK is the, say, the weighted adjacency matrix, right? And so this is 0 if there's no coupling. So, and then we have a coupling function GK that tells us how these two nodes XK and XJ interact with each other, right? And what do we want to do now is we want to go higher order, right? So in this case, maybe I do this on a simplicial complex-like thing, and I have a third order term. But I want to have higher order terms of general forms, right? So I'll adopt this formalism because it's very, very general. I can write this expansion for a long time. Yeah, so if you tell me some of your dynamics, I can probably write this in this form. Okay. So, all right. So now let's start with some sort of philosophical musings here about. So what is the complex dynamical system that we want to understand? basically there are these nodes. They all have this sort of dynamics, right? And there are two aspects that we need to understand if we want to understand this system. And that one is the topology, the scaffold on which the dynamics run. So this is sort of the constraints, if you want, on the interactions. And then there's a local dynamics, right? And typically, we assume that this local dynamics here, this F, right? It might depend on the node states and so on, but the functional form is sort of similar, right? So maybe it's similar on every edge, it's similar on every third order edge. Because if every node would do something completely different, everyone, of course, everyone of us is unique somehow, right? But then we couldn't learn anything from this, right? So if everything is entirely arbitrary, good luck with that, right? So we have to make some assumptions. Okay, but now there are sort of two key questions, right, that come up when you go to high order. And we've seen a couple of answers over the last days already as well. And then the two key questions are like, can new things happen if high order interactions are included? I think in general, the answer is yes, right? And then the question, the second one, which is more what I'm after at this talk, is, are those high order interactions really necessary to explain certain phenomena, right? So in some sense, this is what I'm always asked, like, so why do you need this stuff? Why do all these complications? Can't I just do graphs? Because I love graphs, right? So why should I learn about hypergraphs? So again, two parts, structure dynamics, and let's start with some sort of more philosophical reflections about stuff, questions that I get when I try to convince people that they really should look at higher order systems. And I want to start with this little quote here, which has been attributed to many people, but I just took Fermi as one of a kind here. And so it says, like, before I came here, I was confused about the subject. Having listened to your lecture, I'm still confused, but on a higher level, right? And I think this is kind of a nice quote. You can also find it associated to, I think, Niels Bohr. I got the quote from there's a book by Oxendahl about stochastic differential equations, and it says there, it was written on a board in front of a lecture room in Copenhagen somewhere, right? So it's, yeah, so Jürgen Joost, historian authority confirms. At least the book aspect is confirmed, yeah. Yeah. So we have both. Okay, in Norway. Okay, yeah. There you go. Already correction here. But yeah, thank you very much. So it is in a book by Oxendahl. You can find this quote attributed. Okay, so here we go. Let's think about this. So, okay, so let's start with a very, very simple thing. Linear diffusion dynamics on a hypergraph. So what we want to do now is to consider a dynamics that's defined on a 3 uniform hypergraph. So they're just triangles, if you want, just 3 node interactions. And they have this very, very simple form, no input. So node xi evolves according to this functional form, right? So there's an aijk, so it's like an adjacency tensor. And there's an fi function, and this j and k is basically, so it acts on I, and j and k are the inputs. So if you want, this is a directed hypergraph. And it's the plain vanilla aijk is just 1 if there's a connection, if there's a triplet or not. So here's a very simple observation. Of course, if the function f is linear in x, right, then you can always write this as a network dynamical system, right? So why? I mean, basically, well, you just sum over these indices and you get this thing back, right? And so then what people say is like, look, unless there's no linearity, there is no hypergraph somehow. But of course, I would argue that actually is the wrong word here, because in a way, nothing is a hypergraph anyhow. A hypergraph is an abstraction, is a model. We define things to be of that kind, right? But just to tell you, this is not like, so here, this is a linear interaction function. You do the derivations, And what comes out is basically a new matrix. This is the triangle Laplacian, you can call it like this. So there's a degree matrix that just sums over all the aijk. The summation is a kj, and you get a weighted adjacency matrix. And so in some sense, there is a network representation here, but it's not the same. Network in some sense is a different, right? It's another linear dynamics on a graph. And, you know, okay, what is better here? You could argue either way. Maybe if you're a graph person, you say, okay, graphs are generically simpler than hypergraphs, then you go with a graph view. Okay, but you can also construct example where this is the other way around, right? So what have we learned? So a network dynamics with a linear interaction function can always be written in terms of a dynamical system of another graph, right? So this is in some sense rather trivial linear algebra. So is now nonlinear behavior necessary for true higher order effects in the sense that you cannot write it as a linear system? Yes, certainly yes, that's true. But is nonlinearity enough, right? If we add nonlinearity, out comes the hypergraph dynamical system in some expansion, as sort of Christian said yesterday, and the answer is no. This is not necessarily the case. So here's an example of a contrived system. I made it up, and it's sort of a Kuramoto-like dynamics on a hypergraph with vertex set V and edge set that's just a subset of all the vertices, right? And so how does it look like? So I sum over all the alpha that is, so alpha indexes the hyper edges, right? And basically I want to sum over all the I that are in this hyper edge. So this is my I, right? So I look at all the hyper edges where I is part of, and then I look at all the other nodes, and I take this coupling function, sine xj minus xi, right? And of course, here you can clearly see that somehow, right, the nonlinearity is still pairwise in some sense, right? And so I just sum over it, and this is perfectly representable as a graph. So this doesn't make things hypergraphy, if you want. But okay, here's another argument that I somehow got thrown at. So okay, you're saying now a nonlinear system is not necessary, but Michael, any nonlinear system can be represented by a lifted linear system on an extended state space. And so if you've never seen this, trust me, I think it's really cool math. You should look into it. So this is the so-called Koopman operator trick. And the idea is that you exchange a finite dimensional nonlinear system to an infinite dimensional linear system, right? And so I said, aha, linear equals graph somehow. Therefore, everything is a graph, right? So why hypergraphs? But of course, there's a wrinkle in here, right? And the wrinkle is that, first of all, it's infinite dimensional, so it's kind of tricky to think about it, but maybe you can say, okay, but that's just mathematical complications. You can think about infinite networks as well. But the thing that I think is very important is the semantics of these state variables. Because before we were talking about localized state variables, you could think about it maybe as computing units that were coupled over different things. Now the state variables in general will be delocalized, right? So they will be all over the place. So talking about a network there is tricky in a way. So to give you an sort of exaggerated example, if you were to take this viewpoint that okay, whether the state variables are localized or not doesn't matter to the extreme, you could almost always make the whole network disappear as well if there is a linear dynamics even. Why? Well, just look at a undirected linear, so undirected graph, linear dynamics on top of it, right? Well, let's just do an eigenvector transformation of the coordinate system, right? And suddenly the network is gone, right? So this would be, of course, also, there's still a network, right? You just transformed it into a different coordinate system, and the individual coordinates now, however, are not sort of localized in that physical space anymore. So the network didn't disappear, it just disappears in this particular representation, right? And so that's an important. It's Fourier analysis, exactly. So there's a question, yeah. Yes, exactly. So you could even go back and find another network, right? So what this emphasizes in some sense is that yes, you can interpret every matrix as a graph, as a network, but not every network dynamical system is just a matrix. In fact, it's many matrices in some sense, right? And so the math doesn't care, but let's say the interpretation of your model that cares about it, and therefore I think we should care about it, right? So here's a figure that comes out of a survey with Heather and Chris, and so that sort of emphasizes this thing. So let's say you had a network dynamical system and you were to include higher order dynamical effects. Maybe you end up here, right? But perhaps you do a coordinate change. So for instance, you do an expansion around a periodic orbit, and then you do a high order expansion. Suddenly there's also high order effects appearing, right? So is this now a real high order network? What is it? And I'm not going to be able to give you the answer here, because in general, I think the answer, it depends. This is a difficult question. It's a modeling question. It's about interpreting what your model should do. And so here we go. Nonetheless, I of course still want to attempt this, right? Like try to find the best possible combination, if you want, of these two things, of the topology and the local dynamics. And here's one take on it, and let me emphasize this. So there's one, you can do it other ways. All right, so here's our framework that we came up with. So we consider hypergraphs with a vertex set V and an edge set E, which is just there are M hyperedges, and each is a subset of the vertex set. Let's call the topological order of this hypergraph the cardinality of the largest hyperedge. Right? So just this is the biggest thing around. You may want to keep track of that number. Now, this formula is a bit of a mouthful, but hold on. So what we want to do now is we consider dynamics really as these two ingredients. So we consider this dynamics to be defined by a sequence of interactions functions. So there's the self-interaction function, there's a pairwise interaction function, there's a triplet interaction function. They can all be different, but we assume that for every hyperedge in the network, they're the same somehow, right? So FD, that is, acts on D variables. And because we want to make our lives simpler, we say that this is symmetric in all but the first arguments. So FD has the node itself. This is on what it acts. And then the ordering of the other nodes should not matter. So in some sense, these are undirected hyperedges, right? And so whether I permute it doesn't matter. And every node that is in a hyperedge is also going to be an output and an input node, right? So this is sort of as close as possible as you can get to undirected hypergraph dynamics. And then the formula is basically what I said before. This is just this sort of expansion, right? So this is the first order, the self-interaction, second order, third order, summing over all the hyperedges and getting a coupling. If there's any question, just interrupt me at any point in time. All right. So here's the visual explanation. So what we have is basically we have a topology, and there are the node variables that are dynamical states. And now every F tells us how we do the updates for every of those K, right? And then there's a compound. And what you can actually show, and it's not too difficult, there's these lifting maps. They are linear lifting maps that in some sense, they just pick out the coordinates that correspond to these hyperedges. Then they feed them into a nonlinear function. That nonlinear function is in a much higher dimensional space. And then you have to push it back to the node. You have to pull it, and we sum over all the Ks, right? And this is kind of interesting. Well, I think it's kind of interesting because it has this, well, if this were a linear function, it has this sort of positive semi-definite flavor that you can see in Laplacians and so on. But this F is in general nonlinear. All right, so now I'm going to do some more complicated definitions, and let me just parse this. So now what we want to define is, okay, so how do we guarantee that we don't make this more complicated than we should? So think about this linear example, right? If I do a k equals 10,000 hypergraph and I do a linear, it's still going to be linear. So somehow we want to capture that. So we introduce something that we call the dynamical order. And so we have our hypergraph dynamical system. We have our update functions fd. And each of these update functions generically, right? So maybe it's linear, then clearly you can decompose it into pairwise. But what we're saying is that, okay, let's look for the smallest number of arguments. So we want to compute this update function as a sum of some other functions that just depend on p variables, where p is smaller or equal than d, right? So maybe it just depends on pairwise, maybe it just depends on 3, and so on and so forth, right? So this is always going to be possible, right? Because, I mean, the worst case, well, it's the function itself, right? So then we haven't gained anything, okay? So then we call the minimal p for which this decomposition is possible for all the update functions that we have in our system. We call this the dynamical order of the system, right? So you can already see where this is leading to, right? So this dynamical order will be the things that we're trying to find, and this would then somehow gives us this trade-off between topology and dynamics. All right? Here's an example. Long definitions demand an example. The logarithm. The logarithm of the product of the states. Clearly, you can decompose this as follows, right? With a little bit of logarithm algebra. All of these update functions have dynamical order 2. So graph dynamics would be enough. In fact, so this logarithm trick appears, let's say, in chemical reaction networks when you have like Michaelis-Menten type of thing. So this is one example. And now this is almost trivial. The effective order is almost always the minimum of the topological order and the dynamical order. In certain mathematical, obscure, I should say, but possible, you can make this smaller. Basically, if you don't have dynamics, because these f functions can be different for every d, and I can define them in such a way that this becomes actually slightly smaller. Okay, so but think about this as the minimum of k and p dynamic, and in practice this means this is the difficult object to find, right? Okay, so how to determine the effective order, right? So if you have the functional forms analytically known to you, well, you can try to do this via computer algebra. It's pretty good these days. Or if you want to do algebra yourself, you can do it. I trust you can do it yourself. It would take me much longer, but however, most of the time we don't have that, right? So in many instances we have this, or we could try to check it, but often we don't quite know the dynamics. In fact, so Leonie, she was working a lot on social dynamics, and there are many, many models for social dynamics. And in reality, we just don't know, right? Unfortunately, in social dynamics, also, we don't have trajectory data typically of a lot of people interacting, but have is a way to infer this dynamics automatically as well. And now you should sort of pause for a while and think like, how on earth could this ever work? It works, or it can work, if you have sufficiently many samples of hyper edges of each kind, right? So if I want to infer, let's say, the kth order interaction function, I need sufficient amounts of data to learn that function, right? So either have long trajectory or ideally have multiple, let's say, independent hyper edges of that kind, right? Because if I just have one and a single snapshot, no chance. All right, so this is not magic, but if you have samples, machine learning can provide you an answer. And well, regression, right? Basically, if you don't like this term. So what do we want to do? Basically, we make the assumption that, I already said this, the same type of update functions acts on each hyper edge with the same cardinality. So the the FD are the same for every D. And so we now try to estimate the true update functions FD by FD hat, right? So we're saying that our X dot is M hat, and here, this function now we can learn. We put a function approximator in it. If you happen to know a good basis, a good expansion for your functions, plug that in. If you don't, we are pretty good at function approximation these days in terms of deep learning, right? But if you know, you can do sparse dictionary learning, for instance. So we need a rich repertoire of functions, and I'm now in a computer science department. We do machine learning and we do deep learning. So what do? We use a universal function approximator. That is a neural network. And so this is just a multi-layer perceptron. And we make this sort of, because we will afterwards want to test what's the maximal order. So we use multi-layer perceptrons with, let's say, D arguments or with smaller than D arguments, and then we sum them up, right? All right. So what do we get? We now need to train that model. So what we give our model is as samples of the state vector and the corresponding derivatives. And if you're a numerical person and you say derivatives, this is ill-defined to estimate, and you're right. So in general, estimating this accurately, if it's noisy dynamics, can be difficult. We do it in a relatively naive way. We can tolerate some noise, but if you want, you can regularize this. So this is I'm not going to talk about this basically. So you can estimate the derivatives from trajectories or maybe from subsample trajectories. And just to give you an indication, so here we assume that we have 500 points of this kind in the experiments. And now we need to define our loss function. So I said we want to match the X dot to the M hat. And we also add a little regularization term here to keep our model parameters from not getting too large. So this is a rich regression type penalty. But this is our loss function. This is just now empirical risk minimization. So of course, we hold out some data on which we're going to test afterwards. So there's no magic happening here. And because, unfortunately, in real-world data, you don't know what the true dynamics is, we have to test this with some dynamics that we know. And so we just do some sort of Kuramoto-style dynamics now, where we can regulate the order of the Kuramoto dynamics with this P. We have an epidemic spreading. So this is a typical epidemic spreading, although by no means the only variation of this that you could do. Here, the consensus linear, this is a test case. And then we have an opinion formation model that we call multi-way consensus model. And that is basically working as follows. So what this term does, right, in the linear consensus as well, is that you move towards the average of your hyperedge. And now here's a nonlinear modulation of this, right? And it then basically tells you, like, if you as node I are away from the average, right, then there's an exponential modulation of this. So depending on how far away you are from the average, you're going to move there faster or quicker. So you can put a parameter here as well, but in here is just one. Okay. So now, can we learn the correct update functions? That's the first thing that we want to do. So here, Moto type update function. This is for the multi-way consensus. You can get all the update functions in the paper if you want, but let me explain these plots. So this is the true model order that we put in, and this is the true interaction function. So this is the function F2 in this case, right? And now here comes the trick with the symmetry in the last arguments. So because it's symmetric in all the other arguments, we can just plot the with 2, right? And clearly, you should see a sinusoidal pattern here in the Kuramoto, and indeed you do, right? So this is the true. Now this is the learned function that we learn. Looks pretty decent. If you look at the absolute error, we're still making some errors here and there, and of course the higher the model order, the better the approximation tends to get. But this is now telling the model up front, look, fit me a 2 order dynamic, fit me a 3-order dynamic, fit me a 4-order dynamic, right? And it works also for this other update function. So you can see this is not a Kuramoto model, the same, but the picture by and large remains the same. We make some absolute error, but the approximation is pretty good. There's a question. So the choice of the data that we use is this, right? There are no, I mean, so you can initial conditions. Well, if you start it close to full synchrony, then, well, okay. So you should start it in a regime where, if you're talking about, let's say, system identification, you have sufficient excitation, right? Otherwise, if you only excite certain modes, then at best you can learn those modes, right? Yeah. In this case, I believe we did random initial conditions, so then with high probability, we get all the modes. But yeah, I mean, if you start with a system that doesn't move, you're not going to learn any dynamics. Okay, so now, because these plots are a little bit difficult to parse, right? Let's reduce this to one number. And so this is the mean absolute error of the approximation for different model orders and different dynamics. Kuramoto, susceptible infected epidemics, multi-way consensus model, and diffusion. This is the error, and this is our this is the model order, right? And here you can see what the true what the true model order was, right? So let's focus on the blue one. So the P2, if you put a Kuramoto with 2 and you put model order 2, well, the mean approximate error is low, and then it goes up. Let me just, sorry, am I mixing this up now? So what do I want to say? So I'm mixing it up, yeah. So because you can see that, I mean, basically what I want to say is that my P model is basically the capacity that I have to fit, right? And this is the order I'm trying to fit, all right? And so you can see now, if I have a 4th order model available, I can also fit a 4th order dynamics, but I can't if I only have a 3rd order model or a 2nd order model. And indeed, the 2nd order model is even a bit worse than the 3rd order model, okay? And what you should see here is that in the diffusion case, it's more or less flat. There's not much happening. But now, this is just, again, this is sort of, you have to provide the model order, but we want to select this, right? And how do we select? Okay, here's the same thing now in terms of the trajectories. The blue is the true trajectories that we want to fit. The red is what the model would tell you. It thinks the dynamics is, right? And here, the diagonal should be in some sense the true, right? So it's the model order and is matched. And what you can see here, for instance, is that in some sense the higher order model now overfits, or there's something weird at least, right? And so trajectory-wise, this also looks kind of reasonable. But again, how do we select now the best model? And this is also standard. We don't come up with sophisticated new things. We basically use a panelized or regularized likelihood score. You could do this Bayesian with a prior on the model space. And so we have this basically performance score that we use. So there's the fit of the model that goes in, and then there is if you wish, a prior that prefers models with smaller complexity, with smaller order. And then you get this second line here, and what this tells you is that, okay, now at this, let's look at Kuramoto, right? At the instance of 2, I prefer the blue model, so the 2, so order is 2, I prefer the blue model. Why? Because it has the highest performance score, right? And now it looks nice, Here, diffusion, remember this is linear, so 2 should always be enough, that's correct. And of course, I've skipped this one, right? So there's something wrong. Here, our score would actually say 3 is enough. whereas the true was 4. So if we scratched our hand and then, like, oh, what's going wrong here? And it turns out that there are 2 things that are important. So the first thing is that there were not so many 4th order edges in these networks but there's one thing that was much more important, in fact, and that's the functional form of the epidemics that we have, because we had this 1 minus state times the product of all the other states. And these state variables are between 0 and 1. And so basically, in the regime where you don't have as much epidemic spreading, right, you're multiplying lots of small numbers. This gets very close to 0. And 3rd order approximation, according to our criterion, is then sort of sufficient, right? Even though we did it with 4th order. But we didn't, in some sense, if you put more samples, you at some point should see the green curve rising to the top. And if you have more 4th order edges as well. All right. So take home message. I first, want to, of course, say that high order networks are great. That's why we're all here, right? And they offer a very diverse framework for modeling complex systems. At the same time, so graphs can serve as a data structure for many high order network models as well. But that does not mean necessarily that graphs are all we need. So what I want to say is somehow, ultimately, this is sort of like a modeling is an abstraction question, right? And the utility of your model. So there's this, all models are wrong, but some are useful, right? Of course, we shouldn't make our models unnecessarily complex, right? But sometimes, just because you have a data structure that's a graph, it doesn't mean that it's more natural to look at the system as a multipartite graph. Maybe a hypergraph or a simplicial complex is more natural, right? Well, finally, I presented you one way to determine the effective order of a higher order system. And then why do we want this, right? Because somehow we want to then say, okay, you don't need these higher order interactions here. You can approximate this with a lower dimensional system. And this is, of course, a trade-off between making the topology complicated and the dynamics sort of complicated, right? And we have one, let's say, way to trace out this Pareto front, and there may be others. Maybe you a priori prefer complicated topologies with very, very simple dynamics. And then that's a choice as well, right? It's a modeling choice. So there are many possible future steps. You can not only infer effective dynamics, but also try to now really get a probabilistic model about the underlying structure. You can try to do much better model selection. You can try to do much better machine learning and more sophisticated function approximation tools. You can have state variables not just on the nodes, but also on the edges and on the other things. You can do many, many things. And if you're interested in any of those, please talk to me. And otherwise, I say thank you for your time and happy to take any questions.
Thank you so much for the wonderful talk.
Going back to the coupon operator you expressed, I thought that it shows little linearized parts of your system, and is where you can control perhaps your system, because those parts are the ones that are more approachable. Is something that you agree?
So I'm not sure. So let me repeat the question as I understood it. So you're saying the Koopman operator is basically a good way if I'm close to, let's say, a controllable state space.
Some linearized parts of your dynamical system. So it's where you can act as to control or runtime verification or sort of thing.
Yeah. So I would say morally, I would sort of agree if you have something that's close to let's say a linearizable state space, then the Koopman operator might be easier to there. I mean, the Koopman operator works in general, right? So there's nothing that prevents this from working in principle. But in practice, of course, you want the infinite dimensional operator to be low rank. And that's because otherwise, and in addition, nobody tells you what are the right Koopman modes to select, right? What is the right coordinate transformation? In some sense, this is the magic. I mean, I like to think about the Koopman operator as a lifting. It's the kernel trick, right? And if you have the right coordinate system, things start to look magically linear. But nobody tells you what this coordinate system is, right? And this is the difficult bit. So learning the Koopman operator from data, there's a lot of literature on that. It's not easy. Some people try to learn actually these functions by neural networks as well, which then sort of, in some sense, defeats the purpose of the Koopman operator, that it's interpretable and but yeah. So there's a huge literature, but yeah.
Well, yeah, that's
Yeah,
what
yeah.
I'm working on the latent space
Yeah.
to detect.
Yes, yes. I think there was maybe another.
Okay, let me start with this interesting aspect of the Koopman operator. I mean, does the transfer operate on a function space? And of course, you can always do it that way when you have some dynamics. You look at the associated dynamics on function spaces and look at the transfer operator then.
Yes.
And
Yeah.
and reconstruct it. But that is the practical scheme, of course, is a question that you're asking here. But the other small remark is in your definition. From the very beginning, you should replace decompose by approximate, because that is what you're
Yes.
essentially
Yeah,
doing.
yeah, yeah.
And then again, there's the question of effectiveness of the approximation, which you measure by your complexity term. Otherwise, of course, you can invoke general whatever Kolmogorov type theorems to get all kinds of approximation. But the gist of your message is you want to do it efficiently and effectively.
Yes, I mean, in theory, right, I could write down this decomposition, and in let's say in pure math, I would say, aha, this is the order. In practice, of course, I can only approximate that order. And as you say, then I have to choose also a metric in which I measure my approximation quality. And even there, you can argue whether this is the right metric that we chose. Yeah.
Thank you so much, Michael. And thank you for all the speaker or the afternoon. It's been really enlightening. And thank you.